And what I want to do is share screen and then Google Chrome, share that. Okay. All right. Can you guys see right now downloads? And then last modified was Samuelson process. All right. So what I'm going to do is I want to try to introduce you to a second order difference equation, give you this is practice for you and how to think about this is practice for you to think about solution to second order difference equations. So let's just go through this one by one. I want to install QuantiCon. That's just a bunch of routines that these guys have developed for me, and I kind of like it, like the routines. Then I'm going to do the stuff for plotting. Then I may need to look at a linear state space model. Okay, doesn't matter. I got a warning message. Okay, so the Samuelson multiplier accelerator model is based on these observations. So you guys should be looking at this. What is, there's going to be government spending, consumption, investment, and GDP. So the very first macro identity is GDP equals C plus I plus G. That's a Keynesian identity. So now that means that there are no exports or imports. So there is no external sector. Now, the consumption function is the classical Keynesian consumption function. Let me make it Command Shift bigger. I want to make it big so you can see it. So you see, so first of all, government spending is an exogenous sequence at fixed G. That's just fiscal policy fixed across time. Consumption at time T depends upon gamma, that's an intercept, and A times lagged GDP. So today's consumption depends on what was happening to the economy 1 quarter ago or 1 year ago. Then investment depends on momentum. Let's look at a quarter ago minus 2 quarters ago. So YT minus 1 minus YT minus 2. If that's positive, businesses invest a lot because B is a positive number. If that's negative, the economy is contracting, so investment is negative. Finally, there's a sequence of random variables, and there's a volatility parameter. So is anybody asking me a question?
Just per year.
Say again. Ask me again. I couldn't hear the question.
Just go on, sir.
Excuse me? Help me out. I couldn't hear what people were saying.
Professor, I think it was just like an echo from you speaking.
Okay. All right. So, all right. So what are you going to do? So you're going to plug all these things in, and you end up getting this formula, 28.4. So let's look at it. Because consumption depends on 1 lag and investment depends on 2 lags, you're going to get a second order difference equation where A and B are the parameters. So in my notation, YT equals, this was B number 1 last week, plus B number 2, 2 lags. And now over here, the forcing term, we used to have just a constant. But now we have a random part and a constant. So now we have a second order difference equation that has the non-homogeneous part is a constant plus randomness. So it's the same thing as what we learned last week, and I just wanted to apply it for you so that you could see how to do it. Any questions about how I'm setting it up? So there's somebody in the chat. I think there's an echo on Anmol's mic. Thanks. All right. Everybody, now, if this is a second order difference equation, Morgan, my man, how many initial conditions do I need? Not just
You
one.
need two. You
I-
need the previous 2 quarters.
So I need the previous 2 quarters, but what's the economics of that? That's why you need y minus 1 and y minus 2. The economics is when I have y minus 1, I know what consumption is, but I need y minus 2 to show about investment, whether the economy was going up or down, because consumption and investment and government spending tell me all about GDP. So this is a classic thing that you would be taught in an advanced undergraduate textbook about dynamic equations. But the key idea here is that it's a natural second order difference equation. Obviously, Samuelson won the Nobel Prize. He's one of the great economists of the 20th century. So it was his idea. Now, the stochastic version of the model has GT and this sigma times randomness. So I never told you guys how to solve a stochastic version, but you have enough of an idea of what to do. Because we've done first order difference equations, and you can do a second order difference equation as well. We'll go there. But right now, GT is just a known number at time t, and sigma times epsilon t, this is the randomness depending on the volatility parameter sigma. So this is going to get you some rich dynamics. Anybody have any questions about what I'm doing? So we want to know how to solve the model. So what do? Do you remember about the characteristic polynomial? I said, look, right, z squared minus rho 1 times z minus rho 2, set that equal to 0. So 28.6 right here, what is that? That's solving the homogeneous equation, right? So Morgan, you see where I'm going? Now, if I have z squared minus rho 1 and rho 2, the rho 1 and rho 2 are just some real numbers. I didn't give you what they were. What are the answers? Well, I'm going to write this thing in terms of the fundamental theorem of algebra, and I'm going to say this is equal to z1 minus lambda 1 times z2 times z minus lambda 2, where lambda 1 and lambda 2 are the 2 roots. But do I have any guarantee that lambda number 1 and lambda number 2 are real numbers? No, they can be complex numbers. So what this exercise is showing you is how to think about complex numbers without being afraid. So it turns out that if they are any number can be represented, including real or complex, with as r, which is you think of as radius, times e raised to the I omega. Now, I want to talk about, this is called the polar form of a complex variable. And I want to talk about how real numbers are a special case. What is, when omega is 0, what is I times 0? Amal. What's I times 0, buddy?
0,
0. What's e raised to the 0 power?
1,
All right, so therefore, when omega is 0, this thing is r times 1. Okay, so if it's r times 1, it's a real number, but r is a real number right here. R tells me how far out I am away from the origin. So if I want to, if I'm thinking of the number 10 in my brain, then I can write 10 times e to the I 0. That's the number 10. If I'm thinking about the number negative 10, what do? How do I get negative 1? Because I say I can represent any number, including positive and negative real numbers. So the key idea here is omega is not 0 in this case. is there a special omega that's going to get me, when I multiply I times it, a negative one? E to the I times a special omega gets me negative one. And the answer is pi over 2. So that's called Euler's great equation. E to the negative I pi over 2, that will give me negative 1. Or e to the I pi over 2 gives me negative 1. I'm sorry to go positive and negative because normally, so what is omega? Omega is the angle that you sweep through as you go around the circle in radians. And if I start, it's actually, excuse me, not pi over 2, it's pi. Omega, when it's pi, gets me negative 1, not pi over 2. When it's pi over 2, E, when I sweep up, that's going to get me positive I. And when it's 3 pi over 2, it's going to get me negative I when I raise E to that power. So this is the way to think about complex numbers. A way to think of this is, what's the alternative of writing complex numbers that you're first introduced to when you see these at the end of calculus? You think of A plus I times B, because A is the real part and I times B is the imaginary part. So if I draw those 2 points, I can make a triangle. The hypotenuse of the triangle is how far away the point is from the origin. So the square root of A squared plus B squared is how far away I am. That's my R. So I'm about to show you how to go from rectangular coordinates back to polar coordinates easily. So draw on a piece of paper for yourself something that goes out A on the x-axis and goes up B on the y-axis, or the imaginary axis, and that's A plus BI. Its radial distance is the square root of A squared plus B squared. But it also has swept out an angle, and the angle that it's swept out has a tangent of B over A. So the angle whose tangent is B over A is the omega right here. And when you sweep out a whole pi, an angle halfway around the circle, that's where you get to the negative ones. That's how I know it. Now, what this is showing you is I could have done everything in terms of cosines and sines. That's why I went down a little bit here. And R is just how far away I am. And what I would get is I would get the initial conditions. When I solve this, then I have 2 initial conditions that are going to pin down my complete solution, my exact solution, and C1 and C2 can be complex numbers because lambda 1 and lambda 2 can be complex numbers. But can you see what's going to happen when I raise a complex number to the t power? So go back up here to lambda number 1. Lambda number 1 to the t power means raise r e to the I omega to the t power. So r raised to the t power is easy. It's just r to the t. You know what that is. R to the 100 power. We do it all the time. But what about e to the I omega 100 power? Nope. So here's what's going to happen. I omega e to any power, when you raise it to 100 power, you multiply the I omega. So it says I 100 omegas. So all it's doing is it says go around 100 times by omega. So if omega is a third of the circle, go 100 thirds around the circle. That's what omega is telling you. It's the angle that you're sweeping through with each iteration. So what the complex number is telling you with its magnitude, it's r, how big it is. And if r is less than 1, as r to the t gets to be a bigger and bigger number, it's squeezing. but omega keeps sweeping around. So all that tells you is how quickly it cycles. Omega says go this much through the circle with each iteration of time. So that's why the solution to all difference equations, that's where we were on Wednesday last week, are partly cycles and partly does it explode or does it shrink. So now that's what we want to look at for the multiplier accelerator model. Are there any questions about what I said right now? Because this is, I'm purposely speaking kind of intuitively on this in these examples. So, okay, so what we're going to do is we're going to try to do an implementation of this thing. Did I? Okay, it doesn't really matter. I don't want this. Yeah, I can do this. Sergeant, when I was a graduate student, so remember I was a graduate student 40, this one's going to be 50 years ago, but 45 years ago. This was high tech macro for PhD students at Berkeley. But this is just garbage. It's a picture of a bunch of solutions, all right, whether or not it oscillates or not. But what we're going to do now is we're going to draw pictures. We're going to characterize the solution. And then, all right, so let's look at what we want to do is we want to look at the characterization of the solution for when row 1 and row 2 are given. So what we characterize the case where row 1 is 1.3 and row 2 is negative 0.4. These are real and their absolute values are both less than 1. So what am I going to get? Remember the solution. It's trying to tell you it's going to be lambda 1 raised to the t power and lambda 2 raised to the t power. Since both of those are less than 1, it's going to damp down and it's going to go to 0. So that's, if I just plug in these numbers, 1.3 and negative 0.4, I get this. Now, here's a function for plotting the paths of the variable. So well, again, this is code that he's written for you. And so if row 1 is 1.4 and row 2 is negative 0.1, now what am I doing is I'm going to show you there's going to be a shock. There are going to be some initial conditions, and then we're going to look at convergence. And we're looking at convergence over 50 periods. So this is just like what you did for problem set number 1, but now it's a second week. So you're going to have 2 roots. You're going to have a second order difference equation. So it has to be fed right here somewhere. Oh yeah. So here, I'm giving it y0 is 100, and I'm giving it y1 is 80. So I'm giving it 2 initial conditions, and I say solve this thing forward by using the analytical solutions that we know. Now, I'm going to ask, here's a hard question. I'm going to ask Caleb, because he's my go-to guy with the hard question. If I run this thing again, and instead of having 80 there, if I put my initial condition is y0 is 100 and y1 is 100, what do you think it's going to look like when we plot out the solution looking forward?
Well, I think there won't be that initial shock, right? Because you'll already be approaching like a convergence, because if the 2 periods are the same, it'll be at a convergence point already.
Right. So now what it's saying is we're in equilibrium, or we don't have so much of a shock because investment is 0. Remember, investment depended upon the momentum there. So let's see what happens. So Caleb, you have very good intuition. So you see, you have this looks just like what you did for your original homework. It's just like a first order difference equation now, because there was no disequilibrium coming from investment being crazy. Does that make sense to you? So Caleb, you had good intuition. Caleb, does that make sense to you? That you got it right?
Oh yeah, yeah, it does. It
All right. So then even if I start at 90, not at 80, but if I start a little bit below, so what is it saying? It says the economy was at 100 at the beginning. Now it's down to 90. So, that means that the investment climate is going to be negative. So then it's going to have a negative shock. Let's run it. And you're going to see that little dip. All right. And if I start out with the economy starts at 100 and I bump it up to 110, now the economy is in a boom starting out, but it's got to come back down. So everybody sees, what does a second order difference equation do? Oh, it's coming back down monotonically. Interesting to me. Did I plug in the right numbers there? Yep. Okay. So anyway, I'm going to just start it where it was at 80. And you see, so the key thing is second order difference equation is that the negative part of the economy can carry on for a few periods before things turn around, and then it comes back to long run equilibrium. By the way, what is this long run equilibrium? 125. That shows where the economy goes when everything settles down. Any questions about this? All right, now let's look at this one, the next one. So what it wants right now is it's going to give you some, what will happen if I plug in R1, row 1 and row 2 of 1.53 and negative 9.024. So first of all, where did it come from? It knew it wanted some roots here, and it went backwards from the complex roots to what the original real numbers had to be. So this is just a little trick that Sargent's playing. It says, hey, I want to generate some damped cycles because I don't want this thing to explode when I play the game. So here's some damped cycles. And what I want is, if this is true, then let's find the roots for this thing using all right, what are the roots of the characteristic polynomial where row 1 and row 2 are 1.53 and negative 0.9 plugged in here? NumPy will find the roots. And what it's telling you is the R part is 0.95, and then the omega part is 0.62. So how far is it sweeping with each time through? 0.62. To go all the way around the circle, you have to go 2 pi. 2 pi is around 6.28. So it goes through 1/10 of the circle in 1 quarter. So this thing sweeps through the whole cycle in 10 quarters. And since R is 0.95, it's going to spiral and it's going to get tighter. So they're going to be damped cycles. That's what we can see from this. So let's run this thing for the non-stochastic Y. And here's the picture you get. With the exact same initial conditions, I'm hoping. So the initial conditions were Y0 was 100 and Y1 was 80. Tell me, not Caleb and not Amma, who feels like talking? Anybody want to tell me what you see in this picture right now? All right, so Morgan is going to tell you. Morgan, talk into the camera. What are you learning?
It just it oscillates as we circle around the complex polar.
Okay, so does this look a little bit more like a macroeconomy with ups and downs and the business cycle?
It has, yeah.
All right, and then what do you think would happen, Morgan? Or who wants to talk? Is there anybody who feels comfortable talking? what do you think would happen if I put it kind of near the long run equilibrium, but not exactly there? So I started at like 98. What do you think will happen? So I'm gonna have 198.
Yeah,
So that's a little bit of a downturn to begin with. What do you think's gonna happen? Caleb, you wanna go? Or Amal, you wanna go? Anybody likes talking, or George?
It's gonna be like less cyclical, I guess. It's gonna be around
Less
the
big up and down, but it'll have a cycle in there, right? But it
yeah,
won't be so sharp up and down. That's what
Yeah.
I guess, okay? All right, so all right, so now you see it's only going between 96 and 101. The picture looks the same, but the scale is less. Does everybody get that? And notice what you have here that's different. You're going up above and then down below, up above, and then it kind of evens out. Does everybody see that? So how did
It's
we
sort of
get these cycles? We
because
got
of
these cycles. Yes,
because
help me out.
the overshooting part comes from the y minus 2 part, right? Because if it were
Yeah,
a or more process, it would be like converging gradually to the particular solution, and then because of the y2, we have this overshooting and then coming back and then oscillating, right?
yes. So the key, if that's Doris speaking, Doris is making this important observation. The only possible way we can get cycles is, or and not the only possible, the best way is to have a second order difference equation. Now, there are some cycles that can occur even in a first order difference equation. You remember when I told you if the root was -1/2, then you would go up, down, up, down, up, down, up, down, up, down, right? But this one, you can have cycles that have different periods than just one period cycles, right? But there are, all right, now, finally, can I generate undamped explosive cycles? So the answer is yeah. So what I want to do is I want to start, or undamped cycles. So what these are, how could I do it? If row number one, or if I plot this thing out, if the roots are 0.809 plus 0.58i and 0.809 minus 0.58i, what do you know about these? You know that their radius is 1. So that's why these things go up and down and they do not explode. Okay? So this gives me deterministic cycles for the second order difference equation. Now, it turns out that what Sargent is going to show you right here is that there's a really clever thing called symbolic Python. And what symbolic Python can do, you should know this, it should be in your bag of tricks. So remember this, and I'm glad that it's being recorded. That if you want to have symbols and you say, solve this symbolically. So look at this SymPy, solve symbolic. Hey, stand up because you're a big guy. See, as soon as Morgan stands up, the lights come back on because he's big. That's why I need his body mass in here, okay? Big, strong guy. All right, so it says solve z squared minus r1 minus r2, solve it for z, and it gives you the quadratic formula right away. So it's beautiful because it can just, if you don't like doing algebra, SymPy will do the algebra for you. All right, now I'm going to put this thing in here and just use some symbolic notation, and symbolic algebra Python will do it for you when I say let A equal the symbol this, let B equal the symbol beta, then root 1 is A plus beta, root 2 is minus beta. So it's solving the whole problem for you algebraically. So again, this is even better than ChatGPT because it does algebra and it keeps you from messing up when you do your homework. All right? All right, now, the last thing we're going to do is we're going to do the same thing, but we're going to have stochastic shocks. So let's look at this new subroutine. And that's what you're supposed to do for your homework. So for your homework, we're giving it two initial conditions. We're giving it an alpha and a beta. Those are the two parameters. We're giving it gamma was remember when we went back, that was in the consumption function. I think we're telling it to go out 100 periods, and we're telling it its volatility is 5. So you're given all the parameters. So what this thing is going to do is it's going to spit back the what the roots are, and it's going to plot some numbers for you. So here you are. Oh yeah, so let's see where it's drawing the randomness. And the key idea here is that it's starting to look like real randomness in macroeconomic data just by having a second order difference equation and a little bit of randomness. So let's go and let's take a look at what the Python code is doing. So I would like Amal, I want to start talking with you, and then I'm going to ask Morgan, then I'm going to ask Caleb, and then I'm going to ask George. So here's what I want you to do, because we're learning Python. So Amal, you're there for me? I want you to do like the first line. All right, so what does the def statement do?
It's defining a function.
Okay, and what are your
Those
parameters for your
conditions.
function? Yeah,
The two initial values, the alpha, the beta, and then
gamma, those are the parameters, right?
Mhm.
And then n is gonna, it turns out that's how far out you simulate, I guess. And sigma is the volatility parameter, right?
Mhm.
And everybody knows, so Caleb should know, when you define it this way, there's a certain name, you're given it the values inside the function, but you don't have to do that. You could have defined the parameters before and called the function. Okay, and then Amal, what is this triple quotation? I like it when you define a function. I like it when you have triple quotations. What's it doing?
it's a comment.
Yeah, for Caleb. It's not just a comment, but what happens is if you go y stochastic question mark in Python, it spits this back. It tells the user, hey, this is what this function does. It's not just a comment, but it spits back explanation of this function. So that's good coding. And then finish off, right, and then I'm going to go to Morgan next. So I'll finish off over here. What's it doing?
Okay, so
Well-
it is defining the parameters that new variables using the input variables, the
Yeah, row
parameters.
1 and row 2, yeah.
And then from there,
It's
it's
calling another function, right?
Mhm.
That was called categorize the solution, that those guys, they wrote it above, right? So
Yeah.
it's gonna spit out, whether you're gonna have real or not, that's what it's saying. All right, now I'm going to Morgan now, and Caleb, you get ready. All right, Morgan, start with find the roots of the polynomial. What's it doing?
Uses the numpy function, right, to find the polynomial.
And this is the characteristic polynomial written. Doris, you remember you asked me this. Z squared minus RZ minus R1Z minus R2. That equals 0. It's finding those roots, okay?
Got
All
it.
right, then what is it going to do?
Then it checks if there are real or complex roots,
Mm-hmm.
and then if the roots are less than 1, so if it's less than 1, it's going to become like a stable.
Yeah, but actually be a little bit careful, Morgan. What's that abs root?
Oh,
Abs.
absolute value.
Yeah, so
If it's
now
less
this is a really tricky question. What's the absolute value of 1/2 plus 1/3 of an I? It's the magnitude, right? Absolute value of a complex number is the radius. So that would be 1/2 plus 1/3 of an I. Its absolute value would be 1/2 squared plus 1/3 squared. Take the square root of that. That's what it's checking for.
Okay.
All right, good. All right, so then what else is it going to do? Prints out some stuff. All right, now you tell me the next two, and then get ready, Caleb. You're up next, or Doris, whoever wants to talk. So tell me, what is generate shocks? What's happening?
So it generates, it uses the numpy random normal distribution to generate just a number in the standard normal distribution. And then is the amount of times you're generating a shock.
Yep, it's going to be a whole vector of normal 0, 1 variables.
Yeah.
How many of them? 100 of them.
Yeah.
Right, that's n of them. Okay, and then, all right, Caleb, you're up. Or whoever wants to talk, Doris or Caleb.
Okay, then the next line I think is the defining the function transition. Is that right?
Yep, and what does it take? It takes an
It
X.
looks like it takes an X and a T. Looks like X is maybe like an array. And so I think it's just, you're just giving it that, your second order equation, right?
Yeah, do you guys know what star backslash means? Because that's worth knowing for Python code. Star backslash.
I don't think
So
so.
it's going to return what? All right. So backslash means this got too long. I didn't want to write it on one line. It means
Gotcha.
continues on the line below. All right.
Yeah.
So remember that, because sometimes if it gets too long, you can't see it on your screen. Okay.
Gotcha.
So it's going to return R number 1 times X lagged 1
Yeah.
plus R number 2 times X lagged 2 plus gamma. That was remember, it knows what gamma is. Plus sigma times your shock. Which shock? The teeth shock.
Yeah.
Everybody got that? It's just returning. It's exactly, Caleb, what you said. Just remember the backslash means it continues on the next line. Okay?
Yep. And then you're
Okay,
setting
then
initial conditions. Oh, sorry.
yeah, and that's an array.
Yep.
I mean, it's a list with Y0 and Y1.
Yeah.
Yep.
And then you're passing it in those lines down there. You're doing your
Yeah, so tell me why you're starting with the range 2. Because normally Python starts at 0. So why are you starting at 2 in your range function? And with T is going to go from 2 to N. Why?
because you need, because of how, I think
Two
it's because
initial
of how your
conditions.
list is, right? You have 2 initial conditions.
Yeah. You need to have Y0 and Y1 fed in before you can start
Yeah.
anything going. Right? All right, and then what is that YT dot append? Just append, and so you're going to, and finally you're going to
Oh, yeah.
return YT. It's going to be a big list. Then you're going to plot it. Okay, so that's what it did, and that was our answer. So does that thing look realistic to you? All right, Dorj. Now, what do you think about? You want to talk, Dorj? Now, are you
Yeah.
okay?
I'm here.
So does that look realistic to you? Like a little bit like macro, like random variables in the macro economy? Eh?
Yeah, to some degree. If it didn't start from 0, yeah, it looks like.
All right, yeah. Let's start it. Let's start it up. It looks like it's settling around 50, right? So
Yeah.
let's start it around 50. So how could we do that? Yeah. Let's start Y0 is, I'm going to plug it right here. Okay, Dorish? Can you see me on my screen? 50
Yeah.
and 50?
Yeah.
Yeah, I'm going to give it a little bit of action. 50 and 49, just like see what happens, okay? All right, what do you think is going to happen now? Now is it sort of like hanging out? Now is
Yeah.
it interesting?
Yeah.
All right, so does that look like a regular macroeconomic series with randomness?
Looks like a business cycle.
Yeah, it's kind of interesting. So you
Yeah.
see, that's why Samuelson wins a Nobel Prize and he's dead. And you and I are just like learning and we're still alive, okay? Because this is a really smart model. Okay.
So, uh, just one question on the Samuelson's model. So his intuition was, even without like government spending in it, business itself can generate it. Because business cycle is endogenous, right? That's what he was trying to say.
You can have an endogenous business cycle if investment depends upon 2 lags. That was the key. That if people worry about what's the economy changing, how is it changing, and that affects investment, then you can get cycles. That's the deep idea. So
Yeah.
let's do exactly the same thing with now when the economy has complex roots. All right, and then here, do you remember the A and B? The roots are complex with modulus less than 1. Therefore, we're going to have damped up oscillation. And the I don't know what they are in polar form. So I would have to figure out what phi is. Did it plot out phi? No. Okay. Now finally, we're getting near the end of the hour. So what I want to do is I want to do a whole new one where there is a shock to government spending. All right, so what, and again, this is how you would do things in macroeconomics. So here's, so let's define this new stochastic G. Who wants to do the reading? I want to, all right, so Morgan, I'm going to start out with you and somebody who hasn't been talking. So I've always been relying on Caleb, Morgan, Amal, and Dorj. So I'm going to start out just because Morgan is right next to me. By the way, guys, Morgan's ready for the job fair, and he's wearing nice cologne. So he's in good shape here. And he got a haircut. You guys should all see him. All right, so what's this new stochastic stuff? What's it doing?
Yeah, so here we got the same kind of parameters. We got like the Y0, the Y1, so what the economy was at the year before, the alpha, the beta, the gamma, the N distribution.
And the volatility sigma. But now you got something interesting. You got government spending.
Yeah.
And then this is a permanent increase in government spending at time T. So
Okay.
it's like COVID, where they spend money and they permanently increase government spending.
Got it.
All right, so we want to see that. All right. Now, who hasn't been talking? Anybody?
I haven't talked. I can talk.
Okay, is that Hunter?
Yeah.
It sounds like Hunter.
Yeah.
All right. So Hunter, tell me what the next few things are.
I mean, the next few things are like the stuff that we had done in like the previous example. It's just setting up, like getting the roots and determining if they're complex or not. And then,
Yeah, so that's all from above.
yeah, it's
And
all
then the
from above.
epsilon, still got, a whole bunch of shocks. This is
Right, yeah.
typical for simulation. Just generate some shocks. Oh, by the way, if I run this computer code one time and then another time, is the picture going to be the same?
No.
No, because the randomness will be different, okay? But there is a way of making it replicate by seeding the random number generator. Okay, now, what about the transition, Hunter? Same thing as before? Yeah, I
Yeah, I
think
don't
it
see
is.
any GTs in there, yeah, so it's the same.
Yeah, and then there's a little G in here, right? I don't know if G was there before, but they're paying attention to government spending.
Yeah.
Okay.
I think G was there before, yeah.
Okay, good. All right, now tell me what's happening down here. For T in the range 2 to N, we did that before.
Yeah, to account for the initial conditions, start at 2, and then
Good. If G is 0,
okay, yeah,
there
this
is
is
no
different here.
Okay, so this one, if it's identically 0, just do the appended transition, okay?
Hmm.
All right, if G is not 0, and we haven't given it a duration, still do the same. Okay, so just append transition YT.
Okay.
All right. Otherwise, if duration equals permanent, then for T less than the GT, that's the time the government kicks in. So this would be like 2021 or 2020 for COVID. Append G is 0. After that, append what? Your increase in your permanent
Right.
government shock. All right. And then there is one there. You can also give it one off for duration. So what's this one? If T equals GT, append the transition G equals G. Otherwise, there's no government spending. So you see what he's doing here? He's just keeping track. There are 3 cases. There's no shock to government spending. It always stays 0. There's a permanent shock that starts at G sub T, or there's a one-off shock. Everybody see what's going on? So when we run this thing, what do you think is going to happen? So I plotted this. So it's saying government spending is T, permanently starts at time 20. All right, so what happened? Can you guys see at 20, this economy jumps up and kind of wiggles around, and it's at a new equilibrium. And how much was that permanent increase? in the government spending 10, and it stays duration permanent, what would happen if I made this increase 100? What do you think it would do to the picture? Anybody have any ideas?
Get kind
Be a
of
reverse shock.
It would be like a big jump up, not just 10. It would be a huge, I imagine, it would be a huge increase. Yeah, so you see it goes up to 600. You see, so here, this is what Trump did and then Biden did. They had this huge government spending because they wanted everybody to be better off after the COVID. What would happen if you elected Fisher? And I couldn't help give you a little bit of COVID spending, but I'm not a generous guy. What do you think if the permanent government spending is only $1 at time 20? What do you think is going to happen? Just a small increase at time. Well, at time 20, a little bit. You see here, we're transitioning into the long run equilibrium, and at time 20, you get a little bit of action, but not a lot.
What if there was a
All right, so a decrease in government spending. Let's start out with I don't think this thing is, let's say it's -10. I don't know what's going to happen. It's going to push it down, is my guess. Oh, yep, there you go. So if you elect Morgan as your governor of California, and he cuts back on the size of the government, this is what's happening in Argentina right now with Milei. Negative government spending brings the economy back down, but you still have cycles, right?
Yeah.
Okay, so I'm going to stop my screen share. And then in a second, I'm going to say goodbye to you guys. We're back in action on Thursday, and we'll do the homeworks for Thursday. Please send me the recording if you get it locally. I was surprised I was unable to record. I don't know what the story was. Maybe I didn't authenticate as a professor. All right, so what you guys learn? What's the main takeaway? Who wants? Hey, let me ask Fiona. Are you still here after all this time? I want to say no woman has spoken, and it's bad. It's bad to let the guys all talk.
I'm
Fiona, you there?
still here. Yeah. Yeah.
All right. So what's your takeaway? What did you learn? And Cody, you're next. We went for an hour and a half. What'd you learn? So Fiona, what was a big takeaway from these two lessons?
I
Kernel
learned
estimation.
I would say that like the Samuelson model has two lags and just shows what GDP is and how government spending affects like the cyclical changes and bringing things up and down.
Okay, so do you agree that this course is called dynamic statistical modeling? Where are we doing stochastic modeling? Dynamic stochastic. Did we have randomness? Did we have dynamics? Were we learning something today for dynamics?
Yes.
Randomness. Okay, and I hope so. You guys could all work. You guys are all going to get excellence on your homework. Thanks a lot, Cody. What's your takeaway? What did you learn about kernel estimation? Go back to the very beginning where I was having all my technical problems. What was the thing that came away for you?
For kernel estimation, and I was still trying to like understand it a little bit, but it's like we're able to apply sort of like
Do you agree that if I give you, say we do a sample of who's going to win the New Hampshire primary, what are they doing right there when the pollsters ask that? They're asking a question. Do you like Trump or do you like Haley, right? So what are they estimating when they ask that kind of question?
I guess we're trying to estimate like the distribution of who's going to say for one person or the other, perhaps.
Yeah,
Or
not distribution. They just want to guess what's the probability somebody's Trump versus probability somebody's Haley. And that's actually a Bernoulli 0-1 variable, right? What's the probability Trump or what's the probability no Trump? All right. That's, you see, they have in their mind 0-1. But would you be interested to see all the distribution of opinions of all the people all through New Hampshire, how much they like all different candidates on a multi-dimensional scale? Now that would be harder to estimate. So you wouldn't, and the distribution could be love Trump, hate Trump, right? It's not Trump, yes, Trump, no. I really, really hate that guy. I really, really love that guy. So a distribution is telling you a lot more information than just yes or no. Would you agree with that?
Yeah, definitely.
All right. All right. What about the takeaway for you for the Samuelson multiplier accelerator model? What'd you learn?
Well, for that one, I really enjoyed it because we're able to like visualize sort of like how those imaginary numbers come into play, and we begin to see like those dampening factors. So like what I took away was that given different initial conditions, we're able to sort of visualize how these markets come into play, like the fluctuations and how they kind of stabilize after a certain period of time due to like the autoregressive, I guess, properties
Good.
of.
Good. I appreciate that. I think I did do a better job because the main difference in the second half is I had actually a manual mouse, so I could actually operate my computer slightly better. All right, and I'm going to say, are you guys going to be around here on Thursday? I hope you guys didn't like all take vacations in Switzerland or something. All right, and then Kate Mahoney, you have any closing words to say goodbye to everybody? Kate, are you around?
Yeah, I'm here. Like what I learned from the lecture.
Yeah, what do you learn from the lecture? And tell everybody to get here on Thursday, all right? So I don't have to do this again.
I learned that the kernel estimation is good when you don't have usual properties in your distribution. And I liked that you gave examples like the rainfall and slow. I thought that was very good to visualize.
Yeah. Actually, it's good that you mentioned it. You know, when they say, oh, we have a drought, that's a crock because it's not normally distributed. A drought here means like no rain or 3 inches of rain the whole year. But if you have 10 inches of rain, the rain distribution really is spiked around 14. And there are drought years, but it's like once every 20 when there's 3 or 2 inches of rain. But there's lots of years when it's 8, 9, 10. And there's some years like last year where it's 35 or 40. This year is a normal year, actually. It's going to be around 14 to 20. So thinking it's a normal distribution rain is crazy. Okay. Anyway, Kate, tell everybody, will you? Parting words from Kate. Get here on Thursday so I don't have to do this and don't look like a moron with my old computer that I had to go grab out of my office. Okay.
Okay.
All right. Thank you guys for putting up with me. I appreciate that you're good students and you're engaged in the class. Thank you.